Hey everybody, it's Ripley back again. We're going to talk about an alternating series today. Now, this is a powerhouse of a series. It shows up a lot for those of you that are taking the AP exam. It's really important because we're also going to talk about error bounds or estimating sums with alternating series, which can be super, super helpful. Okay, so let's talk about what an alternating series is. An alternating series sums and goes from 0 to infinity of -1 to the n b sub n. Now, typically we look at series as a sub n, but alternating series are so important, excuse me, that they have a B sub n designation. It's like, oh, this guy's special. It shows up a lot, and it's also really, really useful. Okay, so an alternating series, let's remember, if you're freaking out and you're like, what the heck? How's this thing work? Well, just think of anything, right? Think of, or let's do it like we always do. Just look at it and list some terms. So the first term, -1 to 0 is going to be 1, so it's going to be b sub 0, and then minus b sub 1, and then plus b sub 2, and minus b sub 3, plus dot, 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 etc. It goes on infinitely. Now, again, remember, n does not have to start at 0. This could be -1 to the n plus 1. All kinds of crazy things can happen. The thing is, it has to change signs. Notice, minus, plus, minus, plus. I guess there's a little plus right there, right? So, for example, I got to have sums n goes from 1 to infinity of -1 to the n over n. And this guy is going to be what? It's going to be -1 plus 1/2 minus 1/3. You see where I'm going with this? Plus 1/4 minus dot, dot, dot. Okay, now there's something called the alternating series test. Alternating series test, or AST. It's so simple. That's the coolest thing about alternating series. Is they're really easy to deal with. They're elegant and they show up a lot. The alternating series test is really simple. It's only 2 parts, and the way that it works is as long as I have an alternating series. So given -1 to the n b sub n, if the limit as n goes to infinity of b sub n is equal to 0, that's part 1. Part B, and b sub n plus 1 is less than or equal to b sub n. In other words, this implies that b sub n is doing what? Is decreasing. As long as it's decreasing, if these 2 things happen, then guess what? -1 to the n b sub n as n goes from 0 to infinity converges. Diverges else. You can kind of figure out, like, for example, if I take the sum as n goes from 0 to infinity. Let's keep this simple. Oh, wait, first things first. Let's deal with our alternating harmonic. So it's an alternating harmonic. Let me change colors real quick, and I'll work over in this little sidebar, or in this in-between spot. So let's look at as n goes from 1 to infinity of -1 to the n over n. Well, first things first, it's clearly an alternating series. We've already listed a few terms. We can see that they alternate, right? So let's check. Does the limit as n goes to infinity of, now notice that this is just b sub n. It's not the -1. The -1 thing just makes it alternate. It makes it change signs, all right? What we're worried about is everything that isn't the -1, and this thing has got to change signs every single time. If even once it goes negative, positive, negative, positive, 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 negative, negative, so you're screwed. Done. You're no longer an alternating series. Now, if you got a finite number of those, you can always remove them. You know how this works. All right, so let's check. Limit as n goes to infinity of 1 over n, you guessed it, is equal to 0. Smiley face. We know b sub n that 1 over, well, I'm getting ahead of myself. I apologize. Remember, part B is we got to show it decreases. In other words, I got to show that b sub n plus 1 is less than or equal to b sub n. Well, b sub n plus 1 is just 1 over n plus 1, which is clearly always less than or equal to 1 over n for every n greater than or equal to 1, right? Do you agree with that? It's easy. Guess what? Our alternating harmonic, diverges. Whoa, I said harmonic in my brain, and I wrote divergent. It's converging because these are both good. Yay. Now, let's look at a different one. What would happen if I said like n let's go -1 to the n plus 1, just for giggles, times n over n plus 1. All right, let's list some terms and see what happens. So the first term, when n equals 0, this is going to be what? 0. Cool. What's the second term? When n equals 1, this is going to be 1/2. When n equals 2, this is going to be minus 2/3 plus 3/4 minus 4/5 plus ... Right? So I don't, this is kind of tricky. I can't really tell if this thing converges or diverges, right? I know that it's alternating. So let's just check it. Hey, first things first. Limit as n goes to infinity of n over n plus 1. Well, what's that equal? Uh-oh. That's a rational function, right? Degree at the top is 1. Degree at the bottom is 1. Ratio of lead coefficients is, you guessed it, 1. Not equal to 0. Sad face. Part B, now we could relatively easily show that this thing we don't even need to. I don't want to make this thing 3 hours long proving this. How would you show that? Let's have a quick dialogue about B. How would you show that this thing was decreasing? Well, you could take a derivative. Remember, n over n plus 1 is equal to f of n, which implies that f primed of n is equal to what? We could do it really quickly. Let's just do it. N plus 1 minus n all over n plus 1 squared, right? Let's see. Low d high minus high d low. That's easy. All over low squared. And this guy is just equal to 1 over n plus 1 squared. Oh my goodness. This thing isn't even decreasing, is it? Because these guys cancel. Oh goodness. It's always increasing. Well, that's kind of a drag. Is that true? Do we like that? -1, right? Is that a mess? Let's see. Let's make sure I didn't screw that up because I don't like my low d high minus high d low all over low squared. Yeah. So we end up with 1 over n plus 1 squared for every n. This implies increasing. Another frowny face. Okay. However, let's look at this one because this is pretty important. Do you realize that out at infinity, if n over n plus 1 goes to 1, that implies that this series becomes -1 to the n plus 1 times 1, which just turns into -1 plus 1 minus 1 plus 1 minus 1. Again, out at infinity plus ... You may say, well, Ripley, it's -1. What? Well, -1 plus 1 is 0. Well, then it's 0. But wait, 0 minus 1 is -1. Okay, then it's -1. Wait, but plus 1 is it? You see where I'm headed with this, right? It's impossible for this thing to converge because it's always bouncing, ping-ponging back and forth between two terms. Okay? Okay, so that's the alternating series test. Super easy to use. Remember, you can use calculus to show that a series is decreasing as well just by taking the derivative. Again, the marriage between the sequence and the function becomes really, really useful. All right, let's talk about an error bound. All right, if we've got an error bound, so I've got this sum, -1 to the n b sub n. It doesn't really matter where I start this. I can start at 0 and go to infinity. I can do all kinds of tomfoolery with these numbers as long as that guy's infinity. I got a -1, and it's not to like the 2n, right? Because -1 to the 2n would just be 1. So be careful of that. Be really tricky. Okay, let's assume that this guy converges. Smiley face. What does it converge to? For example, if I have n goes from 0 to infinity of -1 to the n over n. All right, again, let me list some terms. It's going to be 1 minus a half plus a third minus a fourth plus a fifth, et cetera, et cetera. Okay? Now, here's what I want to do. I want to try and figure out what this thing converges to within a reasonable amount. Okay? But let's not get too crazy. Let's do a little theory first. Now, think about this. On a real number line, what do? Let me change colors here so we can see this kind of pop. What we do is we pick a first term, which this would be b sub 0, but I'm going to call it b sub 1. And we know that b sub 1 is always s sub 1, right? And I'm going to assume that it's positive, so I'll put my 0 over here. Now what happens? I subtract b sub 2. So let's, just for giggles, let's call this distance is going to be b sub 2, which I'm subtracting from b sub 1. And that gives me S sub 2, right? Because B sub 1 plus B sub 2, which is technically negative. So think of it as B sub 1 minus B sub 2. Gives me S sub 2. I'm going to change colors again. Let's go to purple. Now what do I do? Well, I go, we know that B sub 3 is going to be smaller than B sub 1. Or excuse me, well, it will be smaller than B sub 1. But it's also smaller than B sub 2. So I'm going to add B sub 3 to S sub 2, and that'll get me up here. And we're going to call, oops, that's B sub 3. We're going to call this S sub 3. Let me change colors one more time, maybe a couple more times. All right, now what happens? Well, I've got B sub 4, which we know is smaller than B sub 3. So this is going to be B sub 4, and that ends up here as S sub 4. One more time, just because we're having so much fun. Let's do it with orange. All right, now a little bit smaller. And then we'll put B sub 5 and then move up here, and we get S sub 5. Now, what's happening here? Let's go with this guy. What we end up doing is we end up ping-ponging back and forth, 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 until we get to some S here. Okay? And that's our sum. Remember, the limit as n goes to infinity of S sub n is equal to S. Right? That's our sum. That is the worst color ever. Sorry, you guys. Okay, now I wanna propose something. Do you agree that the error, let's see what we refer to as all of this. Let's say, for example, that I just added up the first 5 terms, right? The first 5 terms. Then what we would say is everything else that remains, this is my error, right? This is what I missed. Now you will see this written as R sub n, which can be a little bit confusing, especially when n starts at 0 or it starts at 17. So I don't really dwell on this all that much. All right. All I want you to understand is that all this remaining stuff is R sub n, which is your error, not erron. What the heck's going on here? Is your error. It's how much you're off by. Because if you stop here, then everything left is what you missed, correct? Okay, so let's think about this for just a minute. If I were to say, I know that S is going to live somewhere between S4 and S5, true? So let's think about this. I know the distance between the actual sum and S sub 4 would be what we refer to as R sub 4. That's my error. That's how far I'm off by, correct? Now, what else do I know? I know that R sub 4 is always going to be less than or equal to S sub 5 minus S sub 4. Now let me elaborate. Let me elucidate you on that one. Let's do the absolute value of that. We'll do the absolute value of all of these because it can get confusing otherwise. S sub 5 minus S sub 4 is that distance, true? But S sub 5 minus S sub 4 is equal to B sub 5, isn't it? S sub 4 is equal to B1 plus B2. Whoops, I gotta respect my negatives, don't I? Is equal to B1 minus B2 plus B3 minus B4, right? If you think about that, right? S sub 5 is going to be B1 minus B2 plus B3 minus B4 plus B5. If I subtract this, what am I left with? S sub 5 minus S sub 4 is equal to B sub 5. Now, what did I just say? I just said that the error, if I go out 4 terms, is going to be less than or equal to not just the difference in the sums, but way more easily the 5th term, right? S sub 5 minus S sub 4 is just B sub 5, and we're there. So what I can say is the error bound for an alternating series is always going to be less than or equal to, well, what I just said. It's always going to be less than or equal to B sub n plus 1. Now, let me show you an example. Let me do this. I would like to approximate, let's see, let's go as n goes from 1 to infinity of -1 to the n plus 1 over n cubed. All right? And I want to approximate this thing out to thousands. All right? I want to get as close as I possibly can. So let's go approx to 1/1000th. Within, let's go within. I'm being a little bit lazy here. Sorry, you guys. Within 1/1000th. All right, well, let's list some terms, just like we always do. When n equals 1, I got 1, right? Because it's going to be 1 plus 1 is 2, negative 1 squared is positive 1. All right, so let's see, then what do I have? Negative 1/8 plus 1/27 minus 1/64 plus 1/125, right? So this would be n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. Minus, can I do 6? I don't even want to do 6. Minus dot, dot, dot. Okay? Now, we know it converges. Let's make sure that, that it converges. I know that the limit as n goes to infinity of 1 over n cubed. I don't need the negative 1. I don't care. It just confuses me. 1 over n cubed is equal to 0. Got to have it equal 0. Yay. Part B, I know that 1 over n plus 1 cubed is less than or equal to 1 over n cubed. Yay, right? I don't need calculus to show this. This is for n greater than or equal to 1. So it definitely converges by AST. Make sure that you cite your test, always. However, now I know it converges. I want to approximate it to within 1/1000th. So how far out would I have to go? Okay? Now I'm gonna think about this for just a sec. How would I do that? Well, I know that r sub n, the absolute value of that, is less than or equal to 1 over n, let's go, 1 over n plus 1 cubed. But really, honestly, because the n plus first term, right? Let's not do that. That gets confusing. I apologize for that. Let's just go b sub n plus 1. Because I don't know go away. Because I don't know how far out I'm going to have to go. Now, I am going to use my fancy schmancy calculator because I'm not great with cubes. But watch, I'm going to add some terms to this, and let's change colors. All right, so I'm going to add some terms, and then I'm going to show you how this works. Let me get into my calculator here, because I must admit that 36 times 6 is 2. I knew that. I'm being an idiot. So this is going to be minus 1/216, right? 49, let's see if I can do this in my head. 49 times 7 is what? 343, right? Plus 1/343. 64 times, what's 64 times 8? 512, right? Right? So I've got minus 1/512. And then plus 81 times 9 is 729. 1 over 729. And then minus 1/1000th. Now, wait a second. Do you agree that b sub 10 is equal to this guy? I want to approximate the sum to within 1/1000th, which means if I'm going to do that, I simply need to add up 1 minus an 8th plus a 27th minus a 64 plus a 1/25th minus a 1/216th, which apparently I can't remember today. Sorry, not enough coffee. Plus 1/343 minus 1/512 plus 1/729. Now I stop here because the error bound says that I need only sum up to the values before this value is equal to or less than the error that I want to be. If I add up n equals 1 through n equals 9, in this case, I am guaranteed to be within 1/1000th because this is my error. This guy right here is my error. And that's because, now if I said 1/100,000th, we'd have to go a heck of a lot farther out, further out, wouldn't we? But I said 1/1000th, which is pretty neat. Okay, cool. So the moral of the story is, in most cases, don't try to solve this algebraically. Just list terms, because when you're solving for errors, the numbers are gonna shrink really quickly. In other words, the denominators are gonna get big pretty quickly, and we need to only go out as far as one term before we hit the error that we want, because r sub n is always less than or equal to b sub n plus 1. So b sub n plus 1 in this case, b sub n plus 1 in this case is 1/1000th, which is what I wanted. So I need only go out to 1/729th, add everything up, and I'm done. That's pretty cool. I mean, think about that. It took me 9 terms to get within 1/1000th of the actual value. If you wanted to get closer, you go farther out, right? It just makes sense. The closer you want to get to the true value of the sum, the more terms you have to add in. But because it's an alternating series, we know discovering the error term or finding the error value is super easy. Let me do one more thing and then we're done. Okay, I promise. Do you agree, hopefully, that 1, the number 1, is within 1/8 of the real value of this alternating series? 1 minus an eighth is 7/8, right? So I know 1 minus an eighth is 7/8. I know that 7/8 is within 1/27th of the real value of this series, right? Now 7/8, oh goodness, am I really going to do this to myself? 7/8 plus 1/27. Let's see, 140, what is that? 189, what am I doing? Sorry, let's see, 189 plus 8 is 197, 160, 2/16, right? I lost track of it. Anyway, if I were to take 7/8 and I were to add 1/27th to it, right? That would be within 1/64th of the actual value. 7/8 is 1 minus an eighth, and then if I add 1/27th to it, I get whatever that god awful monstrosity was I was just trying to calculate in my head, and I know that's within 1/64th. Let's do that, just because you guys won't respect me if I don't. 1/27. What did we say that was? 140, 189. This is 189 plus 8, which is 197. Ooh, I was right. 160 and 56 is 2/16, right? So this is, what is that? Where? Oh, that's plus 8, sorry. 197, 2/16. So I know that 197, 2/16, I think that's what I said, wasn't it, is within 1/64th of the actual value if I let this thing go all the way out to infinity. Anyway, that's a neat trick. It's very, very helpful, and you're going to use it often. It is the most often used error bound on the AP for those of you who are taking APs. It's also the most often used error bound for any Calculus 2 class where you're learning about error bounds and you're dealing with them within the context of series. All right, enough of me yapping at you. Thank you for your time and attention. I look forward to seeing you in class tomorrow.